let's actually implement this in some code now. So let's now implement some simple scaling or resizing in OpenCV. So OpenCV uses the cv2.resize function with the arguments listed up here, but let's actually use this function to get a feel of it. So firstly we load our image, and then using the resize function, it takes our input image, none, which I'll discuss later on shortly, fx and fy. These are the factors we want to scale by. So what we're telling it here is that we want to scale our image by 3/4, so 3/4 the original size. And the reason we set it at the same 0.75 here is that we want to maintain our image ratios. So by default, I said it uses interlinear as its interpolation method. We're actually going to try intercubic, interarea, and we're actually going to change the dimensions here that we resize to. So this actually allows us to resize exactly the dimensions we want. So you'll understand that shortly when we actually implement this code. So let's run this code now. As you can see, this is the picture of the Louvre I took, and it's actually smaller than the original images by 3/4 its size. This one is much bigger, so it's twice its size, and this is using the intercubic, which is actually a slower method of interpolation. However, the resizing looks decent quality as well. And this is the one that's skewed, so we actually set the dimensions here. So let's bring this into this view here. So we actually set the width to be 900 and the height to be 400, as I previously showed in the code here. Similarly, we can actually skew in one dimension, or I should say resize differently in one dimension. So we implement something that looks like this here, which is sort of compressed horizontally here. Okay, so that's it for resizing. It's actually a pretty basic function. So we'll now move on to some other topics in OpenCV. So we're going to take a look at a technique, another technique for resizing I should say, called image pyramiding. And what that is, it's shrinking or enlarging multiple copies of an image, as we can see right here. And what that does, it basically allows us to create multiple scales of an image, several scales, several visions in fact. And that's quite useful in object detection when you want to be resilient to different scales of an object. So let's look at implementing this in our code. So the code for implementing image pyramids is actually quite simple, and the bulk of the work is just done in this function here, which is pi down and pi, or pyr I should say, up. So what's happening here is that we load our input image, and pyr down actually converts in this image to an image that's half its size, or 50% the original dimensions. And vice versa, pyr up actually takes this image and makes it twice its size. So what's going to happen if we put smaller into a pi or pyr up function is that we're going to get back an image that is exactly the same dimensions as the original image, but you will see a key difference when I run this code. So here is a smaller image. As we expected, it's 50% smaller. However, when we run this smaller image into the larger image, you may be able to see it in the video here if your stream is good quality, but it actually is quite blurry, and that's because we're upscaling a smaller image here. So that shows you how with resizing images you actually tend to lose quality, so be careful with that sometimes. Okay, so that's it for image pyramiding. If you ever wanted to create multiple copies of a small image, you can actually put this into a loop, like a for loop or while loop, and maybe just run it a few times and it keeps generating smaller and smaller images. So cropping images is something fairly straightforward. I imagine most of you have done this in Microsoft Word or using your iPhone or any image editing software. It basically refers to extracting part of the image that you want, hence removing the excess. So in this example here, we just want the center of the rooftop of the Louvre here, and that's what we get here. So let's take a look at how we do this in OpenCV. So OpenCV actually doesn't have a direct cropping function. However, it's still easily done using NumPy, and that's done in this line right here. So what NumPy allows us to do is that we can put our image array right here, and then using the indexing tools, or I should say methods in NumPy, we define a start row to end row, then a start column to end column, and that separated by a comma, and that basically extracts the rectangle that we wanted wanted to crop out initially. So to define the start row and start column, we actually we load our height and width first, and we actually take 25% of the height and 25% of the width, and then 0.75, so 75% of the height and width. That gives us the exact center point of the louvre, as you saw in this previous slide here. So I've just approximated what those dimensions should be. So by saying start row at 25% here, I've just said that this distance from here to here is 25%, and this distance from here to here is 75% of the image. And similarly for columns here. So you can play with those values if you want. You can enter actual pixel values. I just did this to make it a little easier to modify. So let's run this code and see how it works. So original image, and this is our cropped image. It actually works fairly well. So let's sort of try to overlay this here so you can actually understand a bit more what I did here. So by saying 25% row width here, I'm saying the start position of the rows you want to extract starts here. So that's 25% point, and the 75% point starts here. Actually, these are columns, not rows. And similarly with rows, 25% starts here. As you can see, it's 25% from here to here. And the 75% value starts from here to here. So that's exactly how we get this cropped image here. And if you ever need to use this cropped image for anything else, it actually stores it as cropped, or we store it as a cropped image here from our NumPy indexing. And that can be used for many other things going forward. So that's it for cropping. So let's get into some arithmetic operations using OpenCV. So what arithmetic operations are? They're basically adding matrices to our image array. And by adding matrices or subtracting matrices from our image array, it has the effect of increasing brightness or decreasing brightness or intensity. So to do that, we actually have to first create the matrix that we want to add or subtract to our image. And NumPy actually has some built-in functions, one called np1s. This allows us to create an array which is of this dimension, which is the same dimensions as our image here. And we assign the data type to unsigned integer 8, which is what OpenCV uses to store our image data. And we multiply it by a scalar 75. So if you wanted to see what this looks like, let's just copy this line here and run it separately in a different cell. And let's actually just print it here. And there we go. So as we see, it's a matrix of 75s here. Of course, it follows the same dimensions as this image here. So using the cv2.add function, it adds these two matrices here. Now to use this function, this and this image, or array I should say, has to have the same dimensions, which is why we followed and copied it into this np1s function here. And likewise, we do it with the subtraction function here. So let's see how this looks when we actually run this function. There we go. This is our darkened image here, substantially darker. And this is our brightened image here. What's important to know is that, let's say we did 175 here. What do you think would have happened? Let's run it again. This one is even darker, which means that values that were bigger than 175, these are the only ones that show up now because everything else goes to 0, which is why it's black. And similarly, there's a lot of white points or very light colors here. What happens is that when you add 175 to these points, it actually reaches 255, which is white. As you can see, it sort of has the effect of clipping highlights in some areas here. Please note that we can't ever exceed 0 and 255. So when we're adding matrices to our image array, keep that in mind, that you will get some clipping, which is what we saw in the black and in the white images here. So let's start doing some bitwise operations. And I call it bitwise operations and masking because that's essentially what you will be using these bitwise operations for. They are quite handy when you have to mask images, which you'll see later on in this course, but for now we'll just introduce the topic. So firstly, let's create some shapes here. So we're going to create a square and an ellipse here. Now, you may be familiar with creating a rectangle or square, I call it here, because it's the same dimensions I decided for this one. However, an ellipse is slightly different. It doesn't actually follow the same standard as a circle. You can check the OpenCV documentation to get some details. I won't go into it in this chapter here. It's going to take up too much time. However, let's just run this function and we see it here. So this ellipse or circle I've created here is actually not a full ellipse. I've set the parameters to create sort of a semi-hemisphere type image here. So what we're going to do now, we're going to overlay these images and using some bitwise operations to illustrate the different type of operations that we have. So let's get to it. So let's start doing some bitwise operations. And I call it bitwise operations and masking because that's essentially what you will be using these bitwise operations for. They are quite handy when you have to mask images, which you'll see later on in this course, but for now we'll just introduce the topic. So firstly, let's create some shapes here. So we're going to create a square and an ellipse here. Now, you may be familiar with creating rectangle or square, I call it here because it's the same dimensions I decide for this one. However, an ellipse is slightly different. It doesn't actually follow the same standard as a circle. You can check the OpenCV documentation to get some details. I won't go into it in this chapter here. It's going to take up too much time. However, let's just run this function and we see it here. So this ellipse or circle I've created here is actually not a full ellipse. I've set the parameters to create sort of a semi-hemisphere type image here. So what we're going to do now, we're going to overlay these images and using some bitwise operations to illustrate the different type of operations that we have. So let's get to it. So let's actually run some bitwise operations on the images we just created. So by doing that, we use these OpenCV functions, bitwise AND, bitwise OR, bitwise XOR, and bitwise NOT. If you're familiar with logic gates or just general programming, you'd understand that what these things mean. However, it's always good to illustrate it in our images itself. Keep in mind that square and ellipse has to be of the same dimensions here, which is why we created the canvas initially at 300 by 300 pixels. So let's run this. So before we run this, let's just get a refresher of what our images look like. So let's run the AND command. What do you think is going to happen? Exactly. Well, I hope you assumed this would happen. This is the intersection of only those two images here. And by intersection, I mean these are the only white areas. And keep in mind these statements here, they work when you have a binary type image, either black or white. Otherwise, on a grayscale image, it's not exactly going to work like you imagine. You can try it on your own. However, I'm illustrating the concepts of these bitwise operations here. So this white area here is the only parts of those two images that intersected. So let's look at the OR bitwise operation. Exactly as we anticipated. Both images are shown here. So this sort of takes the circle and the square and merges them together here. Now the XOR. What do you think XOR is going to do? Let's see. XOR is sort of a weird one. It sort of looks like a reverse, sort of an intersection between these. So what this means here is that anything that's AND in an XOR goes back to 0 or black, and where it remains, where the images exist like an OR statement, it shows up here. So it can be useful for some things. You can maybe later on figure out what you may need it for. And now let's look at NOT. Now keep in mind NOT is different. NOT just takes one image into consideration. So a NOT is actually equivalent to an inverse of an image, and you'll see that shortly. So let's look at what that is. So let's bring it in here, minimize this one. So this is a square run in a bitwise NOT operation. As you can see, it basically inverts the colors, which is actually quite useful in many OpenCV functions, which you will come across later on. So that's our introduction to bitwise operations. Hope you found it useful. So moving on to convolutions and blurring. So the first thing to note here is that a convolution isn't an OpenCV function per se. It's an actual mathematical operation that's performed between two functions, and it produces a third function, which is obviously an output coming out of the original operation. So this is sort of illustrated here. We have an image here, then we run it by our function through a convolution, and our function here is of a certain kernel size. And what do we mean by kernel size? Well, this grid here represents a 10 by 10 image or pixel image here, and this is a 5 by 5 kernel. So what this does here, the convolution basically operates at 1 pixel at a time. So I'm operating this kernel here at pixel 2. So the convolution basically operates on this pixel, but it takes into consideration all the pixels around it in its calculation. You'll see why that's important when we get introduced to blurring, which is what we're about to do now. So blurring is an operation, which you may have obviously figured out, that blurs an image. So you can clearly see here, this is a sharp picture of an elephant I took at Colchester Zoo, and this is the blurred image of the elephant. He's now, or actually she's now, quite blurry. So this is an example of a kernel matrix here. This matrix is 5 by 5, and we multiply our kernel matrix by 1 over 25, and that's how we normalize. That's called normalization of our kernel matrix, because we want all the elements in this matrix to sum to 1, which I mentioned here. Now, the first blurring method I'm going to introduce you to is OpenCV's filter2D. It takes an image and runs it past the kernel here. So we're about to introduce that in our code, so let's go to our code and do so now. So let's look at this blurring in our code here. We're going to use the OpenCV filter2D, which is the most basic form of blurring we can do in OpenCV. And we're going to do it by using a 3x3 kernel of 1s that we normalize by dividing by 9. So we're going to see the effects of blurring an image with a 3x3 kernel, and then by blurring it with a larger 7x7 kernel, which we also normalize by dividing by 49. So let's run this code and take a look at the blurring effects. This is our original image. You can see the elephant creases quite clear, so it has a lot of detail in this image. So let's run it by the 3x3 kernel. And you can see it's definitely blurred. It's not a substantial amount of blurring, but it's definitely noticeable when you compare it to the original image. So let's now take a look at the 7x7. We expect a lot more heavy blurring, and that's exactly what we see. This is probably what a person who needs high prescription glasses might see. So that's our first blurring algorithm. We're going to take a look at a couple others now. Right, so if you scroll down over here, you'll actually see some more blurring functions that are available in OpenCV. So the first one we're going to use is actually a box filter. So it's called the CV2 blur function, and it's an averaging filter. What it does, it averages the pixels within a box that it runs for each pixel. So it puts the input image here, then it takes the kernel that we defined here, this is the box size, and averages out all the pixels here. So it sort of introduces a heavy blurring effect. It's actually quite a drastic blurring effect, which we'll see shortly. And that's why there's also the Gaussian blurring here. So what this does, instead of having a uniform box filter, it actually uses a Gaussian box filter. I'll show you what a Gaussian box is in the slides, but for now just imagine it's not going to have such a harsh effect as this blur function. Now median blur also uses a box filter type that I mentioned here. However, it doesn't actually average out everything in the box. What it does, it finds a median value of all the pixels in that box, and then it actually puts median value as that pixel. So it's sort of a nice balance between this and averaging. Sorry, this and Gaussian. And lastly, we have bilateral blurring. Bilateral blurring is actually quite useful, and what it does, it actually preserves it removes noise quite well and strengthens the edges in the image. So let's take a look and run this code and you'll see what I'm talking about. So this is an averaging box filter here. You can see it has pretty much a uniform type blurring effect. This is a Gaussian blurring here. Now the Gaussian blurring would actually, on the same size kernel, would actually be less blurring. But I've used a 7x7 in this example here. And this is the median blurring here. Now if you notice, median blurring sort of has a kind of painted type effect to it. And that's because it's finding the median value in little segments of the image. So if you wanted to ever introduce sort of like a painted type effect, maybe a median blur would be quite useful. And let's take a look at our bilateral blurring here. Now as you can see in bilateral blurring, it's actually sort of a anti-aliasing type effect on this image. But what you can tell is that it definitely does preserve vertical and horizontal lines strongly here. But areas like the ears and different areas in the elephant is actually quite blurred. However, you can see vertical lines here are actually quite strong. So here's a slide summarizing those different types of blurring we just saw. So these are the same notes I just discussed here on each of the 4 blurring methods. However, I told you I'd show you what a Gaussian kernel looks like. And this is exactly what a Gaussian kernel is here. So you remember previously before in these other kernels, everything was the same value here. However, Gaussian kernels have a peak toward the center and they slowly peter off toward the edges here. This is sort of a 3D representation of what a Gaussian kernel looks like, and this is a matrix form here. And again, we normalize by a sum of all the elements here, which in this case is 273. So heading back to our IPython notebooks, there's one last image blurring method I just wish to discuss, and that's one called image denoising. This is the OpenCV function here. Fast N1 means denoising colored. It's quite a mouthful here. And what this does, this actually originates from computational photography methods. And as you know, using cell phone cameras and digital cameras, there's no way those tiny camera sensors can match the noise levels of complex, big DSLR cameras. So what they use to compensate is these complicated algorithms that sort of try to get the best or optimize the noise level so you don't see all the green in the image. So when we run this function, it actually takes some time, so I've just run it in the background. You get this nice, very clean looking image here. So that's the effects of running this algorithm. Now there's quite a few variations here. I won't get into the details exactly right now. These are some notes on the parameters here. This is filter strength, and these are some of the components you can play with. And that's it for blurring. Let's move on to sharpening, which is the opposite of blurring. So let's quickly discuss sharpening. Sharpening, as you imagine, is the opposite of blurring, and it actually strengthens and emphasizes the edges in an image. As you can see in this example of sharpening here, the edges here are normal, what you would see with your own eyes. However, in this image, all the edges here are much more pronounced, vertical, horizontal, edge along the rooftops, everywhere. So to implement sharpening, we actually have to change our kernel and actually use the cv2.filter 2D function. So the kernel for sharpening actually looks quite different here. However, as you can tell, it still sums to 1. And that way we normalize our image. Otherwise, if it didn't normalize to 1, your image would be brighter or darker, respectively. So let's run this simple sharpening example in our code. So again, we load our image, and then we create our sharpening kernel. So as you saw before, we have -1s in all rows here and columns, except in the direct center where we have 9. So if you were to sum all the elements in this matrix, you'd actually get 1, which is exactly what we wanted, which means it's normalized. And to run or implement the sharpening function, we use cv2.filter 2D to implement the sharpening effect. So we take the sharpening kernel and the input image, we run it, and we get our sharpened image here. So let's take a look. And there we go. This is our original image, and this is our much sharpened image. And as you can see, just like the image we saw on the slide, all the edges are much more pronounced. Sort of looks a bit artificial, but you can play around with your kernel matrix and try your own sharpening matrix. There are ways to actually get a much nicer looking sharpened image here. Okay, so let's now talk about thresholding. And thresholding is actually a very important OpenCV function that is quite useful, and you'll find we use it in many of our mini projects going forward. So what exactly is thresholding? Thresholding is converting an image to its binary form. But what does that mean exactly? So if you look at the function, it's the cv2.threshold function, this gives you an idea of what to expect. So imagine we have the input image here, a threshold value, which is very important, a max value, and a threshold type. So I'm just going to quickly illustrate what happens in this function here. So let's look at this grayscale image here. And also please note, all threshold functions use grayscale images. So images need to be converted into grayscale before thresholding here. So this is a grayscale image. It goes all the way from 0 to 255 at the bottom here. And let's assume this is our midway point, 127. That's our threshold value. So, and max value here is a value we want to set everything above that threshold to. So in this example, if this line here is 127, everything above it, going to 255, becomes 255. So this portion here becomes white, and this portion above here becomes black, which is 0. So there's different forms of thresholds, which we'll see in the code, but that just illustrates exactly what's happening here. There's also a type of thresholding called adaptive thresholding, which we'll come to in the code as well. And you may have noticed I used the word binarization here. Binarization or thresholding refers to the same thing. It means we're converting a fully grayscale image into just 2 points, a max point and a low point. Traditionally it's 0 for the low point and 255 for the max point, so white or black. Okay, so let's take a look at implementing some of those threshold methods that we just discussed. So as you can see, there's 5 different thresholding methods we're going to use here. Is binary, binary inverse, truncation, trash to 0, trash to 0 inverse. So let's run this code and we can actually figure out exactly what each is doing. Okay. Oh, just to know that I actually set the windows specifically here. It doesn't OpenCV isn't so nice to automatically lay out those windows. There are some CV2 move window functions that allow you to do that, but I'm not going to discuss that right now. So anyway, back to thresholding. So this is our original image here. And remember from the slides I said we set 127 to be the threshold value. So in threshold binary, everything that's below 127, which is our value we use in our code, hopefully you remember that, goes to black, and everything above that goes to white. So threshold binary inverse actually, and understandably, does the opposite, the inverse of that. So everything darker than 127 goes to white, and everything higher than 127 goes to black. Now, trash trunk does something a little bit different. What it does is that it takes everything that's actually brighter or higher than 127 going this way and caps it at 127, which is why everything just stops at this gray shade here and continues along this gray shade. So what about trash to 0? Trash to 0 actually does something of the opposite here. Everything that's actually below 127 actually gets capped to black, similarly to threshold binary here. However, it leaves everything above 127 alone. So it's a nice effect, can be useful sometimes. And trash to 0 inverse actually does the opposite now. So as you can see, it maintains this color here. This is the initial 0 to 127 part, but everything above 127, just like in threshold binary inverse, goes to black. So let's close these windows now, and we can actually just quickly look at the code. As you remember, the input image is the first parameter here. 127 is our threshold value. 255 is the max value we set. That's the value it goes to when it's above that threshold, or vice versa. 0 is actually used in the opposite case for most of these threshold algorithms. And this here, trash binary, this is where we defined the threshold type we want to use. So it's a simple 4-argument function, CV2 threshold. Hope you have fun using it. So you may have noted one weakness of these threshold algorithms is that they all require us to set the value at 127 or whatever value we wish to use. Now that's not that convenient when you're actually doing it with, like, say, scanned documents or anything of the sort. So is there a better way of doing this? And yes, there is. It's called adaptive thresholding. And I have a slide in our presentation. We'll discuss these methods here. But there's quite a few adaptive thresholding methods used in OpenCV. There's adaptive mean trash. There's Ostu's method, which is quite popular. And there's Gaussian Ostu's method. So let's run this code and we can actually see what's going on here. So this is the original image we're looking at. It's Charles Darwin, Origin of Species. So that's the original image. This here is a regular binary threshold that we previously used. As you can see, it's good. It's not bad. But if we wanted to get this text crisper, we would have had to use maybe a lower or higher value of 127. So this is it here with adaptive mean thresholding. As you can see, you can compare directly to this image and you can see the text is a lot more clearer. So without setting a threshold value of 127 or anything of the like, it actually does a better job already. So can Ostu's method do a better job? Perhaps it can. I mean, there's not much difference separating these images, but in my experience, Ostu's method actually is quite handy. What about Ostu's Gaussian method? Again, this actually looks very similar. There aren't a lot of differences between these images here. However, in your own image dataset, you may want to actually play and try these different thresholding algorithms. So let's learn a bit more about the adaptive thresholding methods that we just saw. So the first one we saw was adaptive threshold. And as you remember, the adaptive thresholding has a big advantage in that it reduces the uncertainty in setting a threshold value. So the input, there's no threshold value in these parameters here. There's a max value, which is 255, the adaptive type, threshold type, block size, which needs to be in odd numbers, one of those where the OpenCV quirks, and a constant, another OpenCV quirk, that needs to be set at 5. Well, traditionally 5. You can experiment with different values, and if you get better results, that's good. So let's quickly look at our code again. So these are the values here. So this is the adaptive type, and I believe this is the only type available for this function right now. And this is the thresholding type we use here as well. And these are the block size and the constant here. And that gave us the results we saw earlier. So let's go back to our presentation now. And I actually just misspoke when I just said adaptive thresh means C was the only adaptive threshold type we could use in this function. There's actually adaptive thresh Gaussian C, which as you may remember is the weighted sum of neighbored pixels under that Gaussian window. So let's discuss OS2, which is actually one of the best adaptive thresholding methods. So what OS2 does is that it tries to find, well, it looks at a histogram of the range of intensities in the image here, and it tries to find the peaks or the modes of the histogram here, and then it actually finds a value that separates these histograms, the best value that can separate these two histograms. That way you actually get the best thresholding value here. So in most cases where you have changes in light intensity, I would encourage you to use one of these adaptive thresholding algorithms. OS2 is actually quite good. However, if your application can use a simple thresholding algorithm that we saw before, those may be faster, so maybe you should just go for one of those. Again, it depends on the use case, and you'll see going forward we actually do use different thresholding methods in our mini projects. So let's explore dilation and erosion. These are two very important OpenCV operations and are quite useful in image processing. So the best way to explain this is by looking at examples here. So this is a letter S here. It's a white letter on a black background, which is what the zeros and ones correspond to. You can consider the ones to be 255 if you want, just to maintain the OpenCV standard. So let's look at what erosion does. Erosion removes pixels at the boundaries of an object of an image. What that means is that the boundaries of the object being the letter S here, imagine everything is gone here and on the boundaries itself. That's exactly what erosion does. So we get a thinned out letter S here. Dilation, however, does the opposite. Dilation adds pixels to the boundaries of an object here. So this is why the S becomes much thicker in our dilated segment here. So what about opening and closing here? Opening and closing are actually useful functions that combine the dilation and erosion together. So opening is erosion followed by dilation, and closing is the opposite, dilation followed by erosion. As you can imagine, an erosion followed by dilation would be very useful in getting rid of noise. So imagine if there were some little white specks in this image. If we erode those images and those become thinned out or disappear altogether, then we do a dilation, we actually preserve the initial image here that we want to maintain. So now, dilation and erosion, while simple, actually causes a lot of confusion with first-timers who try to use it, and it all because there's a false misconception about what it does. Now, yes, it does. Dilation does in fact add pixels to the boundaries of an object, and erosion does remove pixels to the boundaries of an object. However, imagine we have a black text on a white background. OpenCV interprets this white as being the object itself. So when we run an erosion here, it's actually going to erode into this here. So erosion is actually going to have the thickening effect of a dilation. And a dilation is going to have the opposite effect. It's going to have the thinning effect that you expect an erosion to have. Because what's happening here is that the boundaries of the image are basically the inner points here. So when we dilate, we're actually making the white bigger on the edges of this O, P, and whatever else in OpenCV word here. So please don't get them confused. It happens quite often. It happened to me actually. So don't feel bad if it happens to you. So let's now look at implementing dilation, erosion, opening, and closing in our code. So the first thing to note is that we actually need to define a kernel, and we define it by using numpy's ones function, data type here, and we have a 5x5 kernel in our example here. So the erode function and dilate function both follow the same pattern here. We take the input image, the kernel size we defined here, and iterations, which is how many times you run it. In most cases, you would never need to run this more than once. However, if you do run it 2, 3, or whatever amount of times, you actually increase the effect. It's like running the erosion twice on the same image. So let's run this code and we'll take a look and see what happens. So this is the OpenCV text which I wrote out in Windows Paint. This is it eroded. As you can see, it has the effect that we anticipated. It actually erodes the boundaries here, making it much thinner. And let's see dilation now. Exactly as we anticipated. So as you can see, dilation adds pixels to the edges here. So it actually, everything appears much thicker, as if it was written with a marker and not a pen. And let's look at opening. Opening is the effect of erosion, then dilation. So as you can see here, because this, when we erode it, actually disappeared these boundaries here, when we dilate it now, it actually misses these things totally, because there is nothing to dilate on the side here. So that's why opening, so that's how opening has this effect on the image here. So let's look at closing now. Now, closing actually looks quite nice, and the reason for that is because closing is dilation first, then eroding. So what we did here actually should get us back something to our original image, and actually it does. If you look at it, it's actually pretty much the same, just barely noticeable. So these operations that we've just seen are actually called morpho operations, and there are actually a few more. You can take a look at this link to view the others on OpenCV's official documentation site. However, they aren't as useful as dilation and erosion in my opinion, but however, you may have a special use case for it, so feel free to check them out. So let's move on to edge detection and image gradients. So before we continue into this section, I want you to think about what exactly is an edge. You may define an edge as being the boundaries of images, and that actually is sort of right. As you can see in this little picture of a dog here, we can understand that this is a dog because the edges are drawn in. We have the edge of the tail, his body, his face, and his paws, so we know it's a dog. So as you can see, edges do preserve a lot of an image, even though a lot of the detail is missing here. So how do we formally define edges? Edges can be defined as sudden changes or discontinuities in an image. And this picture I've drawn here actually highlights this example. So imagine you're moving across this line here. And this is the intensity as we move along this line here. So as you can see, the intensity is high here. Then suddenly it gets low, which is what this trough represents. And then it gets high again. So this dip here represents an edge here. And vice versa, if this was a white line and a black background here and a black background here, we would have the opposite shape here. So that's how we actually define edges here, by finding the image gradients of the intensity changes across these lines here. So fortunately, OpenCV provides us with some very good edge detection algorithms. We're actually going to discuss 3 of the main ones here. That's Sobel, Laplacian, and Canny. Now, Canny is actually an excellent edge detection algorithm, and it's really good because it has a low error rate. It defines edges well, and it's actually very good at picking up edges here. This here is actually a very hard image here for edge detection algorithm to look at. It's of a dark dog, or Rottweiler actually, and as you can see, you can actually make out that it's a dog quite easily here. So I won't go into the details of all of these algorithms because they actually get quite mathematical. However, I'll just give a high-level explanation for Canny edge detection. So what Canny does, it first applies a Gaussian blurring effect to the image. As you previously saw, we did some Gaussian blurring a few chapters behind. And then what it does, it finds the intensity gradient across the image. Then it applies a non-maximum suppression, which is actually removing the pixels that aren't edges in the image. And then it applies some hysteresis thresholds. So if a pixel is within an upper or lower threshold, then it's considered an edge. And you can learn a bit more about Canny edge detection and different edge detection techniques at these links here. So now let's look at implementing these edge detection algorithms in our code. So let's look at implementing some of those edge detection algorithms we just discussed. So the first one we're going to discuss is Sobel edges. And what's cool about Sobel edges is that we can extract vertical and horizontal, vice versa, edges from the image. I'm not going to go into the details of this function. Although this is kernel size, you can adjust this to get different strengths. And this is the input image here. And then we can actually combine both X and Y edges and using the bitwise OR and show them together. Laplacian is run here with CV2 Laplacian, and it's just, there's no threshold or parameter settings Laplacian, it's just a blanket function. And then there's Canny, and Canny is actually quite simple as well. It just takes two threshold values here. So let's run these edge detection algorithms and compare them. So this is our input image. Remember it. These are the horizontal edges in Sobel. These are the vertical edges in Sobel. These are them both combined. This is Laplacian, and as you can see, Laplacian actually identifies a lot of edges, but also a lot of false positives in the sky. So if only there was a way we can tune these thresholds to give us some nice edges. Maybe that's what Canny is good for. As you can see, Canny actually disregarded the sky and a lot of other excess noise, but actually preserved the edges that we wanted to see, which was in the structures. So what we can look at here is in Canny is that we can adjust these two threshold parameters here. I've written up something quickly here. However, just note that these parameters here are gradient parameters. So let's set the gradient parameters that we want to look at to some tighter values. So let's say 50 and 120. Let's go over Sobel horizontal edges, quite nice, vertical edges, combined, Laplacian. There we go. So as you can see, the images looks a little different. It's not vastly different. However, you can play with your thresholds in Canny and see if you get the best, whatever you want as the best edges to represent your image. Okay, so that's it for edge detection. We'll move on to some other stuff now. Let's take a step back and look at affine and non-affine transforms again. So imagine you have an image like this here, where this is clearly a non-affine transform of an original top-down flat image here. You can see the lines here, they're not parallel anymore, and they're actually going to join in some future spot, maybe somewhere up here or further up. So what that means here is that if we have the 4 points here, we can actually use an OpenCV function to actually warp this image here and get an image like this. So clearly we can take a skewed image once we're aware of the 4 points of the corner and get back the original image. So let's take a look at that, implementing that in some code. Okay, so let's look at implementing that perspective transform that we just saw. So remember, we firstly need the coordinates of the 4 corners in the original image. So that's what we actually have here. These are the 4 points here, and we're basically combining it into a points array here, comprised of these 4 coordinates. And then so these are what we call points A. Then we have points B, which is the output, which is the points that let's go back to the image here. These are the points that we want to define here. So that's a typical A4 standard page size. We need to give it that so that it actually knows what to transform it to. So what we do now, we actually use these 2 points, these 2 sets of points here, with this OpenCV function called getPerspectiveTransform. What this does, it actually generates a matrix, and this matrix here is basically the transform that basically transforms points A to points B. And then we use warp perspective, that function you may have seen previously, to actually generate the output, to use this matrix here and generate the output image, which we've called warped here. And this here is the final size of the image we want to see. So as you can see, it actually lines up with this here. These were the 4 coordinates of the output image that we wanted. So let's run this code. And voila, we get the actual warped page here. If you wanted to do something smarter, you'd probably write an algorithm that gets the contour of this image, then automatically gets the locations of the corner points, then feeds it in, and then we run everything automatically. It's actually not too hard to build. There's actually some blogs online that actually do it for you. So we've just seen how we generated a matrix for a non-affine transform. But what about an affine transform? That should be simpler, right? And indeed it is. You only need 3 coordinates to actually generate a affine transform. So similarly, we have points A and B. We actually use a different image here, and there's a reason for that. I'll show you shortly. So we have 3 coordinates for points A and B, 3 coordinates for points B. We use getAffineTransform as opposed to getPerspectiveTransform. And we similarly implement those transforms using warpAffine. We just switch this here with column and rows, which is similar to using the actual dimensions here. We just take it directly from the image, and let's run this code here. So as you can see, these are the shapes that we wish to transform. So let's press any key and continue. And this is the affine transform. As you can see, this affine transform actually rotated the image slightly, didn't adjust scale or anything, but as you can see clearly, all the lines maintain their parallelism here. So that's one of the main points of affine transforms. So I hope you get a feel of using these functions here. They're actually quite handy and quite important when we're doing more complicated stuff in OpenCV. Hi, okay, so you've made it to our first mini project. This is using our webcam to create a live sketch of yourself. So let's quickly run this app and see what it does. So this is me here talking in my bedroom here. This is me waving around. And this is me here with my cell phone being charged at the moment. So you can actually see the code. It's quite cool. So this is our sketch app. It works pretty well, generally. I mean, you can play with the parameters in our app to get it better better to your taste. So let's see exactly how this is implemented. Okay, so here's the code for our live sketcher app. It's fairly basic, although we do introduce some new concepts here. And the first thing we introduce here is creating a function, an OpenCV or image processing function called sketch here. If you're unfamiliar with functions, imagine a function being basically a group of commands here that we call when we run the sketch command over here. So sketch actually does a bunch of processes here and returns an image for us. So it actually combines multiple layers of image processing and just returns the final output. So it's pretty cool. The second thing I want to introduce you to is actually using the webcam. Now, using a webcam in OpenCV is actually quite simple. What we do here, we actually have run this initializing video capture function here, and it basically creates an object called cap. Cap here can be read now, which is cap.read here, and what that does, that pulls an image from the webcam. However, if you run it out of a loop, it just pulls the image at a time and nothing else. So what you want to do is have cap.read running in a loop, and this loop runs continuously, pulling images from your webcam. It should be pulling at the frame rate of your webcam, which is usually 30 frames a second. Sometimes it's more, sometimes it's less, but generally it's either between 24 and 60. And cap.read also returns red. Red is basically just a boolean that defines true or false whether this was run successfully. However, the real meat of this cap.read function is frame. Frame is the actual image captured from your webcam, and frame is what we pass to our sketch function here. And lastly, this little 2 lines of code here basically tells us that the loop only breaks when we press the enter key. So cv2.wait key previously was at 0 before, took any key in. I'm just introducing now, we can actually define a wait for special commands. So in this case, when you press the enter key or return key, it breaks this loop. One other important thing to remember when using a webcam is that we need to do cap.release. Otherwise, again, what happens in OpenCV is that it hangs and actually locks up your terminal, and you have to go to kernel restart to run it again. Okay, so let's take a look at our function here we defined as sketch. This is actually doing the bulk of the work, and it's where we keep all the image processing OpenCV stuff here. And it's actually a very simple function. So let's take a look here. So what it does, we take the frame from our webcam here, pass it to sketch. We then convert it into a grayscale image, and then we apply a Gaussian blur to that image here. The Gaussian blur is basically to just smoothen and clean up any noise in the image, because webcams aren't very high quality in most cases, so they do produce a lot of noise. So once that image is blurred, we pass it to a canny. As you remember, canny was our edge detection algorithm, and these are the thresholds we set here. These thresholds, please feel free to edit and play with them as you see fit. They can give you different results in different lighting conditions. These are what I found optimal to my taste and my lighting conditions, but you may find something different. And once we have canny, you remember canny was a black background with white edges. However, I was trying to illustrate more of like a pencil and paper type thing, so which is why I used Thresh binary inverse to invert and threshold the canny edges here. Now we could have also used some of other inverse functions here, and you may remember we could have used a bitwise not to invert. However, the reason I use this threshold function here is so that we can actually play with this parameter here. This was our threshold parameter, so it gives you some more flexibility here. And what this does here, this creates a mask, and then this function returns our mask back here. So this actual block of code here actually is a variable itself that's returned from the sketch function, which is how we can show it with the imshow function. So that's basically our live sketching app. Something very simple and something you can actually play with on your own. Feel free to actually add more effects as you see fit. Thanks. Hi, and welcome to section 4, where you're going to learn about a very important topic in computer vision, and that topic is image segmentation. So what exactly is image segmentation? So simply put, image segmentation is a process by which we partition images into different regions. So here we have a few simple examples. So looking at this Volkswagen Beetle sketch here, we can see using an image segmentation technique called contours, we've actually extracted all the body parts, or all the major body parts of the car. Maybe we've gone a little overboard in some areas, but overall it's quite nice. And looking at the domino over here, we can see every bounded region in this little domino sketch has been extracted by our image segmentation technique. And moving on to some handwritten digits, we can see every number here has been isolated by our image segmentation technique, as well as in this bottle cap collection. We've identified the circles quite nicely here. So in this section, we're covering quite a few image segmentation techniques, starting first with the very important contours. Contours form a very important segmentation technique in OpenCV, so it's worthwhile we spend some time doing it. It leads us to our second mini project where we identify shapes by contours. We then look at line, circle, and blob detection, which are all pretty important as well, and that leads to our third project where we're actually counting the circles and ellipses in an image. So let's introduce our first image segmentation technique, and that's contours. So contours are the continuous lines or curves that bound or cover the full boundary of an object in an image. So this picture here illustrates this concept quite nicely. Here we have a piece of paper on a black background, the paper being the object in our image, and the green lines being our contours. So these green lines here cover this paper totally in this image. So this is a very good illustration of what a contour is. And in case you're wondering why we actually bother to find contours, well, contours are extensively used in object detection and shape analysis. Okay, so let's begin implementing contours using OpenCV. So let's load our Understanding Contours IPython notebook file here. It's lecture 4.1, and it brings up the file right here. So this is the code for our first contours project. Seems slightly lengthy, however I'll step through each line to make sure you get a good grasp of contours. So let's load an image of 3 black squares here on a white background, which we'll see shortly. The second part of the program you may notice is that we grayscale the image here. Now grayscaling is a key step when you're finding contours, mainly because the OpenCV to find contours function here can only process grayscale images. If you were to pass a color image here, it would actually return an error. So the next set of image processing we do is finding canny edges. Now finding canny edges of the image isn't necessary. However, I find in practice it reduces a lot of the noise that we experience when we're finding contours using the CV2 find contours function. So this is something you can play by ear, maybe experiment with it or not. Just keep it in mind that it actually can help reduce the number of unnecessary contours when using find contours. Okay, so let's move on to our find contours function here. This is the main core of this program. So this function, cv2.findContours, takes 3 input arguments. It takes the input image here, which is our canny edged image. It takes the retrieval mode and the approximation mode. And there are several options in each of these here, which we will discuss shortly. After which, we display our edged image. And the reason I display it for is that I wanted to tell you, or I should tell you, that find contours actually edits this image. If you don't want to edit your image, use this instead here, edge.copy. .copy is a Python function that actually copies this image here, or the variable here. So we don't actually edit the original variable. So moving back to the outputs of find contours, it returns the contours, which I'll explain shortly, and the hierarchy. And later on we print number of contours found in our image, and then we draw the contours on our image. So if you remember in our drawing functions, it takes the input image, it takes the contours, which are points, and I'll explain that again shortly. Then this -1 here tells it to draw either all contours, or we can actually index it to draw the first contour, and delete a comma there, or second contour, and vice versa. So let's keep it at -1 to draw all. This here is the color, and I believe this will be green, BGR, yes. And this is the line thickness here. So let's run this code and see what's actually happening here. Here we have our 3 black squares. These are the canny edges, done very well.